Now, as we continue to dive fundamentally into the mathematical representations of spin, just being able to model spin from a mathematical perspective, there are several observations that can be made. The first one, of course, relating to what is known as equivalent state vectors. Right? Equivalent state vectors. And what this essentially can be represented by is if we consider, for instance, some particle, and again, we'll name this lovely little particle here Bob, right? And let's say we take this particle and consider and tell Bob that his or her spin can either be represented using spin up or some version of negative spin up. And this is where things get quite curious. The question is there a way to distinguish from a measurement's perspective between the positive and negative versions of these spins? And the answer here, the short answer, is no. And if this is just what you're looking for, you can probably pause the video here, but let's dive a little bit deeper into precisely why this happens. And so the reason being, let's say we have some spin up, and we could represent this as a linear combination, a1 and by some vector b1 plus a2, b2. And of course, if we do want to take a look at the negative version of spin up, we just merely take that negative and distribute it as follows. Right? Minus a2, b2. Now, of course, as we know, we do know it's spin up in both cases. Now, in order to distinguish it, our last remaining resort here would be to take a look at the probabilities regarding the chances of getting b1 and chances of getting b2. So let's investigate, say, b1 first, right? So the probability of getting b1 for our positive spin up in this case would be positive a1 squared, which is simply equal to a1 squared. And probability of getting spin b1 for negative spin up in this case would be negative a1. We square, and don't forget the parentheses in this case, and when we square negative, of course, that comes out as positive a1 squared. And simply put, these two are, equivalent. In this case, the probabilities are equal. And what follows is that we can clearly say the same thing for b2 in this case, and we'll use a slightly darker blue for this. So when we have a2, right, and we square that as well, we end up with a2, and the probability of getting a2 is, the probability of getting b2 here would be a2 squared, and the same goes for negative a2. Right, so simply put, from just a generic perspective, for some given vector v, this is indistinguishable from a measurement's perspective. From the negative version of your given vector. Alright, so let's take this interpretation, let's take this observation, and let's go a little bit further. In terms of further, let's consider one more case and ask the question, when is the statement and the claim of having equivalent vectors valid, and when is it not? So using that kind of similar reasoning, let's explore the following set of four vectors. We have positive 1 over root 2 with spin up, plus again its positive version, spin down, and that's our first vector linear combination here. And let's say we have the negative version of both. Negative. Right, and then let's take the slightly different iteration of what we have here. And again, it's negative version. Now, what quite clearly arises is the observation, just based off of what we established earlier, that these two up here, right, these two linear combinations that we have right here are fundamentally equivalent to one another, because if I take this particular linear combination and multiply it by, say, -1 in this case, then I just end up with this right here. The same goes for our bottom row, our second row. In this case, if I multiply it by -1, they should ideally be equivalent to one another. So from a measurements perspective, this row and this row are essentially indistinct from one another. But now let's consider, say, the columns in this case. Let's consider slightly different pairings among these different vectors, these kets, and their linear combinations. Quite clearly, let's take a look at our first version right here. Now, from, just at a glance, you will note that we have merely multiplied only one of our two terms by -1. However, if we consider things from a probability perspective, what is quite curious is the fact that when we take 1 over root 2 and say the probability of getting, let's focus on a spin down here, probability of getting spin down is 1 over root 2 squared for our first one, which is fundamentally equal to -1 over root 2 squared, which is equal to 1/2. So the probability of getting spin down here is 1/2. And the same goes for spin up in this particular case. Now, what's quite curious, and what I do want you to be very careful of here, is that these are not necessarily equal, because when we consider these two linear combinations here, we know just from a glance and perhaps from previous calculations, indeed, that our first version, positive 1 over root 2 and spin up, plus 1 over root 2, positive 1 over root 2, spin down, is fundamentally your representation of spin to the left. And if we take the 1 over root 2 with spin up minus 1 over root 2 spin down, this is our representation of spin to the right. So simply put, if we were to take our particle and measure spin, right, in the direction of, say, 90 degrees, and this is our 90-degree direction, such that based off of what we said earlier, our spin in this direction would be north, and spin in the other direction would be considered south. Then here, this would be our north kind of linear, the north representation, a north vector, and this would be our south. And so clearly the direction and the orthonormal bases that we choose will actually determine the identity of these vectors, right? Because we chose to measure in the 90-degree direction. And furthermore, based off of the direction that we choose to measure in, these states will not be equal, because clearly having north does not equal having a direction in the south, having spin in the south direction, and the same goes, with the left and right kind of. And of course, the same kind of relationship arises with this right here. This is equal to your negative version. Negative spin to the left. This is negative spin to the right. And that same kind of observation arises with this pairing right over here. Alright, so that is it for equivalent state vectors. Today we just very briefly, just to recap, went over just how and when these particular cases of spin, are indeed equivalent to each other, and when they are not. When you have some vector v, this should be, from a measurements perspective, ideally equivalent to -v. However, when you do have a slightly different vector that has a linear combination that is not equal, just to merely multiplying the entire set by -1, instead of having just, for instance, one of your three terms multiplied by -1, one of your two terms multiplied by -1. These are not equivalent vectors. Their idea and their concept of equivalent, despite having the same probability, just centers on which direction you're measuring it in. And so you do have to be a little bit careful when you claim that one vector is equivalent to another, and just ensure that it does indeed fulfill this kind of relationship here. Do not look only at the probability. Also consider the direction you're measuring in. Alright, if you have any other questions, please do not hesitate to visit the Q-munity Quantum Tech website. And as always, stay curious and keep on learning. Thank you.